Let's begin with the foundations. Welcome to another lecture. Today we turn our attention to Protactinium, a metal that is, if you will, the reclusive scholar of the periodic table. Brilliant, dangerous, and almost never seen in public. I am Professor Alexei, and with me is Priyanka, whose questions, as our regular listeners know, tend to make the rest of us think more clearly than we had planned.
Hi everyone, I'm Priyanka. I'm excited and a little intimidated by this one. Rare, radioactive, complicated. That's kind of our show in a sentence, right?
To frame our discussion, Protactinium, symbol Pa, atomic number 91, resides among the actinides. Think of it as a rare book in a vast library. It exists, it is valuable, but it is locked in a climate-controlled vault, and there is a long line of safety paperwork before you may even glance at the cover. Chemically, Pa is a dense silvery gray metal that reacts readily with oxygen, with water vapor, and with inorganic acids, though alkalis are comparatively uninteresting to it. In the solid state and in solution, the oxidation state +5 dominates, with +4 occurring and lower states, +3 and even +2, appearing under very reducing conditions. This reflects an electron configuration we write as Rn 5f2 6d1 7s2, and the relative stability of Pa in a formal 5f0-like description when in the +5 state.
So I guess we can start by thinking about what happens in water. Does protactinium just dissolve like a salt, or does it, do something trickier?
It's important to understand that aqueous Pa is a master of hydrolysis. In the +5 state, you quickly form species such as PaO2+, PaOH2+, PaOH3+, and PaOH4+. All are colorless, and they tend to produce poorly soluble hydrous oxides that sorb very efficiently to mineral surfaces. This is precisely why, in natural waters, protactinium is scavenged out and ends up in sediments. Structurally, in the solid state, Pa often adopts high coordination numbers. We encounter near-cubic 8-fluoride coordination in Na3PaF8, and even a spectacular 14-coordinate environment in the borohydride PaBH44, which forms polymeric helical chains. As a metal, Pa is paramagnetic at room temperature and becomes superconducting below roughly 1.4 Kelvin. The chloride PaCl4 is paramagnetic at room temperature and becomes ferromagnetic on cooling near 182 Kelvin. One could say its electronic personality is, as it were, temperature dependent.
That's unexpectedly elegant and a little scary. I think the stakes here are high in two different ways. On the one hand, radiometric dating. On the other, nuclear systems. Can we say a bit about both?
Naturally. In geochronology, the 231 Pa, 230 Th pair is a mainstay for dating marine sediments up to approximately 175,000 years and for reconstructing past ocean circulation. Because thorium is more particle reactive than protactinium, their ratio carries information about scavenging and water mass movement. In nuclear science, 233 Pa, formed in thorium fuel cycles, is a strong neutron absorber. It is therefore removed from the neutron flux, for example via molten bismuth columns containing dissolved lithium, allowing it to decay to useful 233U rather than capturing more neutrons to make 234U. On safety, protactinium is highly radiotoxic and is handled in sealed glove boxes. The commonly cited maximum permissible body burden for 231 Pa is on the order of half a microgram. That is not a large sandwich.
Maybe the best place to begin is by asking a simple question about the history. Wasn't protactinium once thought of as an analogue to tantalum? How did that happen?
Let's start with the history. In 1871, Mendeleev placed uranium under tungsten and thorium under zirconium, and, lacking the actinide series concept, he left a vacant slot below tantalum, the so-called eka-tantalum. Chemists understandably searched for tantalum-like chemistry rather than for early actinide behavior. Then, in 1900, William Crookes isolated a strongly radioactive fraction he called uranium X. His ether extraction method would become a workhorse of radiochemical separations. In 1913, Fayans and Goering identified the short-lived 234 millipascals in the 238U decay chain and christened it brevium. The long-lived 231 pascals was identified independently in 1917 to 1918 by Lisa Meitner and Otto Hahn in Germany, and by Frederick Soddy and John Cranston in the United Kingdom. Meitner proposed the name Protactinium, meaning before actinium, which the International Union of Pure and Applied Chemistry adopted in 1949, crediting Meitner and Hahn. There were enabling materials milestones too. In 1927, Aristid von Gross produced milligrams of Pa2O5, and in 1934 he isolated elemental Pa via a halide route related to the Van Arkel-de Boer process. The actinide concept, embraced in the 1940s, finally put Pa in its proper company. In simpler terms, once we understood there was an actinide block with characteristic oxidation states and coordination tendencies, the tantalum analogy dissolved. To bring that historical thread to supply and rarity, in 1961, the UK Atomic Energy Authority processed roughly 60 tons of waste to produce 127 grams of nearly pure 231 pascals at a cost of about $500,000. For a time, that campaign set the world's supply, with Oak Ridge later offering the element at about $280 per gram. In nature, most pascals is 231 pascals from 235U decay. Concentrations in ordinary crust are at the parts per trillion level, occasionally reaching parts per million only in certain uraninite ores.
That was helpful to think through, actually. And a personal note before we plunge deeper. Professor, what draws you to an element that hides in glove boxes and footnotes?
Before we get to the complexities, a brief confession. As a student, I enjoyed chess problems where one silent move decides the game. Protactinium has that feel. It sits between thorium and uranium, with intermediate mechanical and electronic properties, and yet a single misplaced assumption about its periodic home delayed its discovery for decades. We observe a blend of subtlety and consequence that to some extent mirrors a Shostakovich quartet. Quiet surface, intense structure underneath. This brings us to our first big question. Why was protactinium's discovery delayed? The proximate cause is conceptual. Without an actinide series, the community hunted for eka-tantalum. Tantalum chemistry emphasizes +5, with hard oxygen and fluorine donors, yes, but its D-block patterns misled expectations for radiochemistry and coordination in Pa. Add scarcity. Pa is mostly present at ultratrace levels. And add analytical challenges. Pa5 hydrolyzes, vanishes onto glassware and mineral surfaces, and presents colorless species that do not announce themselves. Then history intervened. Cranston's early work on 231 Pa was delayed by wartime service, and multiple groups were triangulating from different decay series members. When the actinide framework took hold in the 1940s, the periodic table finally pointed the searchlight in the right direction.
I'm curious about the eka-tantalum focus. If people were looking for a tantalum-like element, did any properties of protactinium masquerade convincingly enough to prolong the confusion?
To elaborate, Pa does share with tantalum an affinity for oxo and fluoride environments in high oxidation states, and it forms pentahalides. That superficial resemblance was sufficient to keep the analogy alive. But the underlying bonding involves early actinide 5F and 6D participation. Polymeric PaCl5 with its planar chlorine pentagons and 7-coordinate Pa is not a tantalum replay. Amusingly, modern work shows that dubnium, a transactinide, behaves more like protactinium than tantalum does. The periodic table corrects itself, but not always on our preferred timetable. Let's transition to another aspect with a counterfactual. What if Mendeleev had conceived an actinide series from the outset, placing Pa among its true neighbors? We can infer that the search would have emphasized uranium minerals and actinide-style separations. Crookes's ether methods might have been directed more quickly toward the right daughters. Aristide von Grosse may have had milligram-scale Pa compounds a decade or two earlier. The naming and decay genealogy could have stabilized sooner. Would this have advanced nuclear science materially? Possibly in the domain of radiochemical mapping and dating methods.
Can we maybe now look at the reactor angle? If classification had been correct earlier, could that have moved nuclear reactor timelines, especially thorium cycles with 233 pascals management?
Theoretically, some elements of reactor chemistry could have matured faster. In particular, the realization that 233 pascal is a neutron poison, to be removed from flux and allowed to decay to 233 U. The elegant molten bismuth with dissolved lithium reduction method might have appeared earlier in principle. Yet critical reactor milestones depend on discoveries like nuclear fission in 1938, neutron economy studies, and large-scale engineering. Earlier correct classification of Pascal would have sharpened the chemical conversation, but would not have conjured reactors before their physical principles were uncovered. If we indulge an even bolder what-if, had 233 pascals possessed a very short half-life and tiny neutron capture cross-section, the thorium cycle would have been simpler, but the universe issued a different problem set.
Building on that, I think the next thing we should talk about is the open question today. How can we deepen our understanding of protactinium's role in geochemistry?
As we continue, recall that nearly all natural pH is 231 p scale from 235 U decay, with a half-life near 32,700 years. This near monoisotopic character simplifies interpretation. In seawater, strong hydrolysis and sorption mean that pH is scavenged onto particles and sediments. Thorium is even more particle reactive, which is why the Pa to Th pair is informative for circulation reconstructions up to about 175,000 years. Open questions cluster around kinetics and context. We need tighter constraints on how pH partitions among mineral surfaces of different types and sizes, from clays to hydrous oxides, and how those equilibria shift with pH and organic coatings. In soils, the partitioning is dramatic. Sandy soils may hold roughly 500 times more pH than their pore waters, and clays or loams can exceed ratios of 2,000 to 1. Yet the microscopic controls on that enrichment remain incompletely parameterized.
What research is needed for deeper insights? Like, if I were designing a project, where would it push the field?
It is worth noting several promising directions. First, systematic adsorption-desorption studies of PADA5 and PADA4 hydroxo species, on well-characterized mineral substrates across pH and ionic strength, coupled to speciation modeling that respects the observed hydrolysis products. Second, field-calibrated measurements of 231 Pascal, 230 T8 in environments with strong particle flux gradients, such as boundary currents or regions with abundant biogenic silica, to refine how particle composition biases the ratio. Third, improved ultratrace analytics using high-sensitivity mass spectrometry to reduce uncertainties in low-activity samples. Finally, redox and solid-state questions remain. The formation and stability of low-valent Pasley compounds in anoxic sediments and their potential remobilization pathways could matter for both natural diagenesis and repository assessments, given that 231 Pascal contributes to long-term radiotoxicity in spent fuel.
So yeah, moving on. Can we briefly note what PAR is not? I've seen occasional confusion online. It's not a fuel, right?
Clearly stated, while 231 pascals and 233 pascals can undergo fission with sufficiently fast neutrons around 1 megaelectronvolt, 231 pascals cannot sustain a chain reaction under practical conditions. Mid-20th century speculations about a critical mass have been superseded by better nuclear data. In consequence, Protactinium has no commercial applications. It is used for research, handled in glove boxes, and acquired at great cost and trouble. One might say, it is the element that sends grant officers to their calculators.
Maybe that's something we can come back to later. For now, can we close the circle with a short recap?
To summarize, Protactinium is a rare, highly radioactive actinide, dominated in nature by 231 Pa. Chemically, it favors the +5 state, hydrolyzes in water, and forms unusual high-coordination solids. Physically, it is paramagnetic and at very low temperatures superconducting. Historically, discovery was delayed by misplaced periodic expectations and by scarcity, until the actinide series concept clarified its home. We considered a counterfactual in which earlier correct classification might have accelerated radiochemical understanding, though not the fundamental physics of reactors. And we outlined open geochemical questions where Pa, paired with 230Th, continues to illuminate past oceans and sedimentary processes.
And, as a related topic for next time, I think uranium would make sense. Its role in nuclear chemistry frames a lot of what we touched on today. Thank you, Professor.
This then completes our present analysis. Thank you for listening. Handle your elements and your metaphors with care.